Welcome everyone on YouTube. So thanks for watching. This is our 50th live stream geometry. So a nice little milestone to reach, halfway to 100. So if you'd like to join future sessions, feel free to email me at mgreenb801@gmail.com. So the sessions are on Sundays at 8 a.m. US Central Time. And for those of you that celebrate Christmas, I hope you had a Merry Christmas. So with that, I'm going to get started. So I'm going to keep doing problems from the Taiwan Team Selection Test until we run out, because I feel like it's a very nice contest and we've had a lot of fun doing it the last couple times. So here is the first problem. So we have a circle with 4 points B, C, X, and Y. So I'm going to have to end up relabeling them. I'll keep BC, but I'll relabel A and B as X and Y. Okay, so here's X, and here's Y. And A is the midpoint of arc BC. Oh no, A is the midpoint of the segment BC. So let me draw those two segments. Whoops, sorry. So L1 and L2 are perpendicular to BC and they pass through B and C. And let's align passing through X and perpendicular to AX. Interesting. So we want to draw the segments AX and AY. And we want to draw the perpendiculars to AX through X and to AY through Y. And we want to look at those 4 intersection points. So let's see how I want to do this. Something like that. So where does Z get used? I'm really confused. I don't see Z. Oh, angle. It's in the final thing to prove. Okay. So we have this point and this point. It intersects L1. So this is Y1 and Y2. Then we have X1 and X2. So X1 is where it intersects L1. So this should be X1 and this should be X2. And X1, Y2 intersects X2, Y1 at P. It's interesting. So we're probably going to want to move the diagram a little bit. And we want to show angle AZP is 90 degrees. Okay. So let me move stuff around a little bit, maybe move B and C a little bit to the right. And X and Y, let me try to find a good way to do that so that you can see these lines intersect. Yeah, I'd like to try to keep, let's see. If I make it like this, does that make things better or worse? No, I want like a wide, something like that, maybe. So I wonder if this point, no, I don't think that point's on BC. I would be very surprised if yeah, it's not. But let me move this whole thing farther to the right so that we can see that point better. Sorry. We also want to see x1, x2, y1, and y2. Yeah, sorry, this is taking me a long time, but I'll figure it out eventually. Let me just zoom in. There we go. That's better. Okay, so this is point P. We want to show that angle AZP is 90. Let me hide a couple things. X1 is not visible. But, can you guys see X1 now?
Yeah.
Okay. I'm going to stick with this diagram unless you guys want me to change it. Right. Let's see. Probably move it down a little bit just to make more room. It almost looks like P lies on X. Okay.
Can you name the center of CXYB?
Oh, the center of the circle? Yeah. It almost looks like BC is a diameter. So yeah, I should probably change that. Change the diagram a little bit for that. Guess that looks okay. So this is point, I'll call it point O. So OZ is perpendicular to XY. OA is perpendicular to BC. Yeah, this angle is such a, yeah, we know O at OZX is 90. We want to show AZP is 90. It almost looks like PX and Y are collinear though. So I don't want to look like that. But yeah, I think it's always going to be kind of close like that. So yeah, these are, maybe it's worth labeling this point. We know that these are tangents to the circle. Oh no, actually is that true? No, they're not tangent. Because it would have to be perpendicular to OY, not AY. Let me see, maybe I can get a little better diagram. That doesn't look that much better. Yeah, you know what? What if I just think of different ways to do the diagram? Might look better if I do that, but then maybe like that. Let's see. So then I would want to draw I guess it's a little asymmetric because x1 and x2 are on like the same side of point X, but
I think diagram was better.
yeah, it
than
was better
axis
before.
between L1 and L2.
Yeah. Yeah, you want X between the two. I agree. Yeah. So then if we want to see the intersection, yeah, I could just press undo a bunch of times, but it'll get there eventually. Here we go. Yeah, we'll just have to know, yeah, because this doesn't look super tangent, right? You can see the intersections here. So this isn't a bad diagram. But yeah, we know DAYX is cyclic. I don't think AZ and D are collinear. Because yeah, we don't know AX equals AY. It looks collinear there, but I don't think it's actually true, right? Because
Yeah, they are not.
yeah. So what's a good way to show this? We want to show angle AZP is 90 degrees. We know angle OZX is 90. So yeah, it's the same as showing OAZ angle OZA equals angle XZP. But I don't think those triangles are similar, right? I would be surprised, although it's possible. So we could try to calculate angle ZAO is 169, and angle PXZ. Yeah, so they're not similar triangles. Or I could triangle PZY. Oops.
No, the length ratios are too different.
Are different, yeah.
PD passes through two midpoints. May be useful.
Ah, good point. I didn't think about that. PD passes through the midpoints of x2, y2, and x1, y1. Yeah, there's no way AX and E are collinear. Maybe there's something special about point E. Let's see. Maybe we'll figure it out later. Okay, so AZP equals 90. Do we know the angle that PZ makes with something else? So we want to show angle OZA equals angle XZP. It's an interesting problem. I must feel like I want to use this args somehow. I just don't know how. Does a spiral similarity take AZP to some other kind of triangle? I don't know. Let me draw the circumcircle DAXY. We know AD is a diameter, so maybe we
can intersect it with EF. That may be useful.
Okay. So AD is the diameter and AG is perpendicular to GB. So basically we want to show that AZGP is cyclic, right?
Yeah.
Maybe there's something special about that circle. Does that pass through O? It looks like it. I actually don't think it does. Actually, now it looks like it does. Interesting. So it looks like, but how can that be? That would mean that angle AOP is 90 degrees. Oh, maybe that's true. Interesting. So yeah, can we show angle AOP as 90 degrees? Yeah, that's definitely 90 degrees. I don't know why though, but it's an interesting fact. So we want to show OP is parallel to BC. Maybe Desargues. I know I just say Desargues. I don't really have a plan, but P. Yeah, that's really interesting that OP is perpendicular to AO. It's parallel to BC. I would not have expected that. And also, we kind of have a rectangle, right? Because if we draw the line OP, then these two will pass through these 2 points, right? So we have this point, and then we have the other point, and BCIH is a rectangle.
No, it's not.
Oh, it's not? Oh, you're right, because
Yeah.
IH would be a diameter. That's my bad. One second, I'll be right back. Sorry about that. All right. Thanks for waiting. All right, I see Dat just joined. Hey, Dat, thanks for joining. So we're on our first problem. Sorry, I just had to step away for a second. We're again doing the Taiwan Team Selection Test. So basically we have a cyclic quadrilateral BCXY, and A is the midpoint of BC and Z is the midpoint of XY. And then we draw these two lines perpendicular to BC, and then we draw the perpendiculars to AX and AY, and they cut those two lines at X1 and X2 and Y1 and Y2. And then X1, Y2 and X2, Y1 intersect at P. And we want to show that angle PZA is 90 degrees. That's the problem. And it looks pretty hard, but we noticed something interesting. So yeah, we noticed angle POA is 90 degrees. All right, let's see. How do we show that AO is parallel to OP? But yeah, I don't know if it's worth extending. So like maybe I could try drawing this and letting it hit the circle at another point. So basically it's like we want to show PO is like the perpendicular bisector of these two. Is that a rectangle? That should be a rectangle, right?
Yeah, it is.
It's like a little bit slant, I guess. Yeah. I don't know if it's worth drawing this point right here. It's weird. That looks slanted for some reason, but it's not. It's a pretty nice configuration though. Yeah, instead of having the perpendiculars to OX and OY, you have like the perpendiculars to AX and AY. So I guess another way we could try to phrase it is X1, Y2, Y1, X2, and this line are concurrent. Maybe that will help somehow. We use Pappas or something. Or we could just try to use ratios somehow. So if we could try to label the midpoints of CH and BI. So we could call it J and K, for example. We want to show JX2 over JY2 equals K Y1 over KX1, right? And then I think that would prove what we want there. Let me check. This is still pretty surprising to me that that is perpendicular. Let me make sure it's actually true. Okay, so it looks like as we move X, yeah, as we move X, P moves along a line. This is a really pretty interesting diagram. Or we could use points E and F instead of X1 and Y2. Like we could. Yeah, it's kind of interesting that E is the midpoint of X2, Y2, and J is the midpoint of CH. I don't know if there's a way we can use that. So can we try to use this args? Let's see. What if we have triangles X1, X2, K, and Y1, Y2, J? So basically that means we want to show I draw Y1J. Those almost look like they concur on here, but I don't think they do. So I think, let me see if I could see that intersection a little better. It's like this point, we want to show D, the line through D and that point is parallel to X1, Y1, and X2, Y2. I think that would do it. I think DL is parallel. All right, and another way of saying that, trying to draw that intersection point right there, the circle with the yeah, it won't draw it. Sorry. Oh, it should work. Yeah. It's the same as saying either DL and M are collinear or DL is parallel to X1, Y1, and X2, Y2. Whoops. It almost feels like it should be obvious to prove, but I just don't see how. So yeah, we want to show DL is parallel to both x1, y1, and x2, y2. Yeah, this is tricky. We also, so I didn't draw these, but we have x1, x, a, b is cyclic. So it might be worth drawing that. Sorry, didn't mean to do that. Let's see, x1, x, a, b. And y2, yac. Do these meet on this line? It looks like it. It looks like they concur.
It's obvious.
Oh, it's obvious. Oh yeah, because this is 90 degrees and that's 90 degrees. And then is there anything special about point N? Not that I see right now. So we have AY2 is a diameter of one of those circles. And AX1 is a diameter of the other. And we know that E and F are midpoints. I don't know if that helps. Wait, so yeah, so Q, let me check the chat. Remove some of the circles. Yeah, hold on just a second, but I'm about to remove it. So if R is the midpoint of AX1 and F is the midpoint of BX1, so RF, wait a second, that doesn't make sense. Oh, F is the midpoint of y1, x1. Okay, yeah, so that's not super useful. So we know that would tell us that RF is parallel to AY1. I just don't know what that does. So yeah, I'm going to delete those circles. Oops.
Can you also delete L?
I delete L, yeah. So if we go back to the ratios, we want to show that CX2, or sorry, JX2 over JY2 equals KY1 over KX1. How do we calculate JX2 over JY2? Yeah, we have a bunch of cyclic quadrilaterals here. So yeah, JX2 over JY2, it seems like there should be a way to do that.
I guess we can go on.
Go on to the next problem. Okay. Okay, so we have two lines BC and EF that are parallel. Whoops. So I'm gonna redraw this in just a second. So draw parallel. Okay, so we have BC. Then EF. I might need to switch these around later. So let D be a point on segment BC, and I is the intersection of BF and CE. And then we draw the circumcircle of CDE and BDF. And we label their centers as K and L. Oh no, the circles are called K and L. So let me move it here a little bit. Okay, and then they're tangent to EF at E and F. Okay, that makes things, that's weird. So they're tangent to EF at E and F. How would that work? Oh, I guess it could be something like this. But how could they both be tangent? Does that make sense? Circles K and L are tangent. Let's see, are tangent to EF at E and F. That seems, I don't see how that could be. Let's see. What if I did this? Like how could, maybe something like that? I don't know. But I don't think just making it smaller is what they want. I think I'll move on to the next problem. You could check that out later, but I think I'm missing something here. Let A, let me read the rest of it. Let A be the other intersection point. Okay.
You should move F and E to the right.
Move F and E to the right. Okay. So like that kind of?
Maybe between B and C.
Between B and C. So
F must be between B and D. Projections of B and D onto the line EF.
okay, so move, make BC a little larger maybe, and then point F just went away a little bit. So maybe
F must be between D and B.
okay. So this one I could try to make it tangent, but oh, they could both kind of be like that. Oh, okay, like that. Oh, but then, so I, okay, we just have to redraw point I. Okay. Yeah, no, good call. So yeah, no, I think we could do this problem then. So those are both tangent.
We can draw ELF again. Is on the perpendicular bisector of CD.
Okay, so E is basically the perpendicular bisector of CD, and F is the perpendicular bisector of BB, basically. Okay, so I'm going to redraw the problem like that. So let me erase everything. Okay, so it's not as tricky as we thought. So okay, so we have a BC. And then I'll just put a point D on it. And then I'll draw the two perpendicular bisectors. And then I pick another point here. And then I draw the parallel. Okay, so this is F And then this is E. And then we draw those two circles. So CDE and BDF. And they intersect again at point A. And then we have to draw I, so the intersection of BF and CE. That's I. DF and K intersect at Q. Okay, so we draw the, whoops. So obviously DFB is isosceles and so is CED. So we draw the other two intersection points. They're K and L. So this point right here is K. And this point is L. And wait, no. This is Q and this is R. I wonder if QDR is isosceles, but we'll find out in just a second. EQ and FR intersect at M. And we want to show I, A, and M are collinear. Okay, so call that point M. Let's hide a couple things. Actually, hide a lot of things. We don't need hide BC. Okay. A couple isosceles triangles here. M is where EQ intersects FR. So that looks like we've drawn everything there. All right. So we have two isosceles triangles. Okay, DQR is not isosceles. You can see from that figure. Interesting diagram. Can we say anything about point A? Is AQ perpendicular to BC? I would be very surprised if that were true. I don't think it can be, because then by symmetry, I think we'd have AR. Yeah, because it can't be. Is there another point that lies on that line? I don't know if it's worth drawing the centers of those circles. Hmm. We could use, let's see, how do we show they're collinear? Desargues. Would I join FE? Yes. Yeah, no, that's a good point. I should show EF. I missed that line. So yeah, EF is tangent to both those circles. You think we can prove that is F? Oh, do you mean the cross ratio AIME or? Yeah, I think you mean that. Yeah, that the cross ratio through the point F and AIM and E. Okay. Let's see. Interesting. So I think would that solve the problem if we knew those cross ratios are the same? I think it would. It should, right? So okay. So I could kind of rewrite it like this. So yeah, we don't know they're collinear, but I could let AM intersect EF at a point. Actually, what is the best way to do that? So how do we show, okay, how do we show those cross ratios are equal? We project through F onto the circle. So it would be like ARF. So basically we want to show the cross ratio FARB is EARC after we project. Or EAQC. And once we know that, is there something else we can project through? Is ACQE harmonic? I'm not sure. Let me check it out. So let me draw the tangents. I'm going to draw the tangents at A and C. And then I want to see if QE passes through the intersection. I'm gonna have to move the diagram a little bit to check that. Yeah, so it looks like it's harmonic. Yeah. Is that obvious? Let's see. Well, another way is we could show the tangents at Q. We just, So like we could let AC intersect EF at a point, and then we could show that that point with Q is tangent. I don't know if there's another way to show it, though. Maybe we could use some medians. Basically, because we could draw the midpoint of CD, right? Okay. So once we know that it's harmonic, then yeah, so then we can project it's ABRF, and then we could project through D, and we'd get ACEQ, and then we could that makes a lot of sense. I like that proof. So let's see if we can prove that AECQ is harmonic. So I think to show that AECQ is harmonic, let's see. So if we could show that AECQ and ACQE are the same, then we know it's harmonic. So let me label the midpoint of CD. Can we show that angle CQJ is DQE? Well, wait, sorry. Oh no, not CD. So what if we project through D? So onto EF. So if we project AECQ through D onto EF, then we get EF. We want to show DA passes through the midpoint of EF. Is that obvious? Let me draw the midpoint.
It is our problem. It's easy to see.
Oh, that.
Yeah.
Oh, because the radical axis theorem, right? Because J has the same power with respect to these two circles, so it has to lie on the radical axis. So that solves it. I like it. Right?
Yes.
All right. I think that might be what you were saying. So, So let J, so we can write up solutions. So let J be the midpoint of EF. All right. So since JE equals JF, then that means the power of J with respect to CDE equals the power of J with respect to BDF. And so that means that D, A, and J are collinear. And then if we project through D onto EF, that's basically how we find out that AECQ is harmonic, because we have, let's see, or ACEQ, or let me say EQAC. That's equal to EF J, and then EF, the point at infinity, which is equal to 1. And that means that AECQ is harmonic. And then similarly, hey Quan, thanks for joining, Quan. And then similarly, we have ARBF is harmonic. Okay, and so now, now I'm just going to write out the calculation that you wrote in the chat. So and then that solves the problem. Let me see how this looks. Let me break this up into 2 lines. See if that works. Whoops, I think I have to do a double backslash. There we go. So FAIME, I'm assuming you guys all know that's like the cross ratio. So you draw the 4 lines from F to A, I, M, and E. And then it's basically the cross ratio of those 4 lines. So this should solve it. AIME, it's A, B, R, F. Because EF is tangent, and then ABRF, we can project that through D, and we get ACEQ. So wait a sec. Did we actually even need that they're harmonic? Like, where in this do we even need to use that they're harmonic? Let's see. Oh, because we're saying ACEQ is the same as ACQE. That's where we're using that as harmonic, right? Yeah. So that solves the problem. So we'll move on to the next one. Nice solution. So we have a triangle ABC with BC greater than AB. And L is the internal bisector. And PQ are the perpendiculars from I don't know if they mean A and C to BL. That might make more sense. So I'm going to do that for now. So that's P and Q. Oops, sorry. And then M and N are the midpoints of AC and BC. Wait, that's weird. So I guess it's not symmetric then, if that's how it is. And then O is the circumcenter of PQM. And it intersects AC at H. And we want to show that O, M, and H is cyclic. This problem actually looks really familiar, so I don't know if we've done it before. But yeah, I feel like I've seen this before. But I still don't remember how to do it, so it should still be good to solve. Let me, before I erase this, I don't know if it's worth drawing like these intersection points with the side. So I'm gonna extend AB, and I'm gonna draw this point and this point right here. Until this thing goes away. Come on, there we go. Call that D and E. Let me move things around. I just don't want E and N to be so close together. I think that looks better. Okay. All right. Oops. Sorry. So we have C, D. Whoops. Just want to show DA. And get that. God. You draw the bisector. I think that's it. Was there anything else I was supposed to draw? So you know MN is parallel to AB. And so MN and Q are going to be collinear. And this is going to be parallel. So basically, we want to show that ON bisects angle HNM. I'm going to change the problem statement just to show that this is to BL. OMNH. So we know what if we draw the perpendicular to ON? Let's see. So PM is parallel to BC. Forgot about that. And QM is parallel to AB. So PMQ has two sides parallel to ABC. It almost feels like I want to extend these two. I don't know if it'll do anything, but so we know angle HMN, right? That's just 180 minus angle BAC. And we want to show that's equal to angle HON. That's one way to do it. I don't know if it's the best way to do it.
Could you draw the midpoint of AB?
Yes.
So if HOMN is cyclic, so the midpoint of AB should lie on that circle as well.
Ah, interesting. So it's a 9-point circle of ABC. So basically that would mean BH is perpendicular to AC. It's interesting. So basically, yeah, we want to show the 9-point circle of ABC passes through O and H. I wonder if OFN is isosceles. Yeah, it looks like OFN is isosceles. So Well, yeah, it would be if the problem was true, so. Sorry. So yeah, I wonder, is it, so we could try to show that BH is perpendicular to AC.
Okay, so I could prove that H is lie on H is the attitude of B to AC.
Okay.
That is because B is cyclic.
Why is that? Because AHB.
Because PHM is equal to PQM
Okay.
is equal to PQM, and QM is parallel to AB.
Okay, so
Therefore,
yeah, so BPHA is
yeah.
cyclic because of that reason. Basically, because BHM is PHM is PQM is PBA, and so
Yeah.
and then okay, so we know H, we know E, F, H, and M is cyclic, and then we just have to show O lies on it, right?
Okay, so
Yeah.
it is kind of easy too. So we gotta prove two triangle FPO and NMO is equal to each other. So OP is equal to OM, right?
Okay.
And FP is a half of AB, which is MN.
FP is half of AB,
AB,
which is MN.
yeah, yeah. So and the angle FPO is 180 minus FPB minus OPQ, right?
Okay.
Yeah, and FPP is PQN.
Okay.
And OPQ is OQP. So FPO is 180 minus OQM.
Okay. So FPO is
Which is,
180 minus OQM.
OQM, yeah, which is 180 minus OMQ, which is OMN. So so the two triangle is like it's
Congruent.
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 Equal. Yeah.
Yeah. Okay. So we could show triangle FPO is congruent to OMN. Okay. All right, I'm just going to write that down before I forget it. So, okay, so let me start from the beginning. So, okay, so basically we know MNFH is cyclic, and then we want to show O lies on that. So that would show OF is equal to ON, right?
Maybe.
Yeah. Okay.
That we prove angle FON is equal to FMN.
Okay.
Yeah, and because two triangle is congruent, so angle FOP is equal to angle NOM. So therefore FON is equal to POM is twice of PQM, and that is ABQ, and that is a half of ABC.
Okay, so angle FON, sorry, FON is POM And POM is twice angle PQM.
Yeah.
And that is that's the same as angle ABC, which is angle FMN.
Yeah. Yeah, and that will solve the problem.
All right. Hold on a second. So, okay, so let me first write the other points. So did we use E and D? I don't think we ever used points E and D. So yeah, I don't need them, I guess. Let me see what happens if I delete that. Not delete that. Okay, so okay, so first we try to show that ABPH is cyclic, so I'm going to write out your proof of that. So let me draw a P and CQ. So you prove it. So we have angle PHM equals PQM equals ABP. And so ABPH is cyclic. And so angle AHB equals angle APB equals 90. And so, oh, it looks like Serdar had to hop off. Oops. So, so that means that F, H, M, and N. So first I'll actually define F. Let F be the midpoint of AB. Actually, I don't even need point F. So I could just say H, M, and N lie on the 9-point circle. Oh, but I use it later. So yeah. So let F be the midpoint of AB. All three of you are from Vietnam, right? Or I'm not sure about Quan, but Quan, are you from Vietnam? Oh, well. But yeah, thanks for joining. Yeah, it looks like a few people had to leave. So, so yeah, we have that F, H, M, and N lie on the 9-point circle of ABC.
Yeah, of course.
All right. And then FPO is congruent to OMN. That's because, so first we have FP is half of AB, which is MN. That's part of it. And then we also have OP equals OM, which is obvious. So and then the angles, angle FOP, trying to remember how we did that. Hold on just a sec, let me remember. So angle FPO we can show as angle OMN because angle FPO is FPA plus APO. FPO is 180 minus FPB minus OPQ. So you can kind of do it that way. So that's how you did it originally. So angle FPO is 180 minus angle FPB minus OPQ. And that's 180 minus FBP. So yeah, that's FPO, and then angle OMN. We can kind of do it. Yeah, it's just an angle chase. So OMN is 180 minus OMQ, which is
B is FBB, and that is PQM minus
I'll just skip the
PQM.
B.
Yeah, minus angle OQB. Yeah, and that is angle OQM.
Okay, 1 sec. So that's
That is 180 minus angle OQM. And that is
OMN.
OMQ.
All right. Thanks for mentioning spelling that all out, which is all right. So, and then I think that does it. So FON is equal to FMN, and so that means FOMNH is cyclic. All right. Nice solution. So I'm going to move on to the next one. I'll just draw that circle.